Hello and welcome to the presentation related to hydrostatics. This is the introduction to hydrostatics, where we will outline some definitions, terminology and units. We'll introduce various densities such as the mass density, the relative density and the weight density, and we'll conclude the presentation undertaking some exercises to determine the weight of fluids within cylindrical tanks. Here's a presentation overview of the hydrostatics introduction. We commence with some definitions, define hydrostatics, the fluid, and the various states of a substance, such as the gaseous state, the liquid state, and the solid state. We then state the formula for calculating the pressure in a fluid, for example, the pressure in a fluid contained within a cylinder, where the fluid is subject to an externally applied force. We consider SI units of pressure and also non-SI units of pressure that are often used. We consider the characteristics of a fluid. We then define various densities such as mass density, symbol lowercase rho, relative density, symbol lowercase sigma, and weight density, symbol lowercase w. Within these first 5 sections, there are various examples and exercises for you to work through at your own pace to try and consolidate your learning. But the presentation concludes with 2 exercises related to calculating weights of fluids contained within cylindrical tanks. Section 6 draws upon the knowledge and equations outlined within sections 1 to 5. And here are the approximate start times related to the various sections within the presentation, hopefully to aid your ease of access through the presentation, but please remember they're only approximate start times, usually rounded to the nearest minute. Hydrostatics, an introduction. So hydrostatics, or the statics of a fluid, is the study of force and pressure in a fluid at rest. Just note for reference, hydrodynamics is a term used to relate to the study of fluids in motion, but we do not consider hydrodynamics in this particular presentation. Introduction continued. So let's define fluid. So the term fluid is used to describe substances that can flow and which have no shape of their own. There are usually 2 forms of fluids, that's a liquid or a gas. Liquids and gases offer negligible resistance to a change in shape. Introduction continued. So a liquid and a gas are distinguished by the following characteristics. Firstly, a gas completely fills the space in which it is contained, shown in figure 1 here. In this particular case, the gas fills the entire container, whatever the shape of the container, whereas a liquid usually has a free surface, shown in figure 2. If we pour the liquid into the container, it takes the shape of the container, but often has a free surface, as shown here. If we now consider a solid retains its shape when placed in a closed container, shown in figure 3 here. So whatever the shape of the solid is retained when placed in a container. Another characteristic to be aware of, a gas is a fluid which can be compressed relatively easily, whereas a liquid is generally considered to be incompressible. Let's consider pressure. A fluid in a closed cylinder, as shown in figure 4, may be pressurized by applying a force, labelled capital F, shown here, to the piston, shown here. If we neglect the weight of the fluid, then the pressure, P, in the fluid is defined by the following formula. So pressure P is equal to the force F applied to the piston divided by the cross-sectional area, labelled as A here, which is the area of the fluid in contact with the piston. So in other words, P is equal to F divided by A. The SI derived unit for pressure, generated from the formula, So that's force, newtons, divided by area, which will be in meters squared. So the formula in the bolded box here calculates the pressure in the fluid P when subjected to the external applied force F. Here's an exercise for you to undertake. If a force of 0.55 kilonewtons acts on a piston having a diameter of 112.8 millimeters, we've got to determine the intensity of pressure on the water in contact with the underside of the piston if the piston is considered to be in equilibrium. In other words, it's stationary. The answer is given in the bracket here. So I'd encourage you to stop the presentation and attempt exercise 1. Here's the formula you need to use to determine the pressure. It's basically the applied force F divided by the cross-sectional area of the piston. I will show you the full work solution on the following slide. Exercise 1, here's the solution. Extracting information from the question, we're given the force applied is 0.55 kilonewtons. That's this force F here. I've written that here as F is equal to 550 newtons, removing the kilo prefix. We're informed that the piston diameter is 112.8 millimeters. So my diameter piston D here, I've converted the millimeters into meters, so 0.1128 meters. I've calculated my area. Obviously this is a circular section, so formula I'm using here to work out the area of a circle is pi d squared upon 4. Inserting the diameter from above in meters, that evaluates to an area of approximately 0.01 meters squared. Finally, calculating the intensity of pressure, more simply the pressure P, that's the force stated in the question, divided by the cross-sectional area we calculated above. So the pressure is 55 kilopascals, or of course that could be 55 kilonewtons per meter squared. Let's consider the unit of pressure. The derived SI unit of pressure is the same as that we use for stress, direct stresses, bending stresses, etc. And that's the Newton per meter squared. And the Newton per meter squared is given the name of the Pascal, denoted as capital P, lowercase a. So 1 Pascal is equivalent to 1 Newton per meter squared, or of course we know that can be written as 1 Newton meter to the negative 2. So like the unit of the Newton per meter squared, the Pascal can be specified in various multiples. So for example, 1 kilonewton per meter squared, which is 10 to the 3 newtons per meter squared, of course, can be written as 1 kilopascal, or 1 meganewton per meter squared, which is 10 to the 6 newtons per meter squared, can be written as 1 megapascals. And within industry, you will find the Pascal is often used for the specification of pressures. Let's consider an alternative unit of pressure known as the bar. Now for pressure, but not usually stress, the bar and its multiples are sometimes used. The bar is a convenient unit for engineers as it's approximately equal to the atmospheric pressure. In other words, atmospheric pressure is approximately equal to 1.013 bar, although that does vary, of course. So for reference, 1 bar is equivalent to 10 to the 5 newtons per meter squared, or 10 to the 5 pascals. But we're expected to use engineering notation, so our powers of 10 should be to the 3, 6, 9, 12, etc. So we often write 1 bar as 0.1 meganewtons per meter squared. And just note the m for mega has the value 10 to the power 6. Let's consider exercise 2. We've got to fill in the missing entries in the table below. So let's consider atmospheric pressure. That can be taken to be 1 bar. So in newtons per meter squared, that's 100,000 newtons per meter squared. That's 10 to the 5 newtons per meter squared. And in terms of pascals, there's 100,000 PA. And 1 millibar is 0.001 bar. And of course, remember that milli is 10 to the negative 3. So 1 millibar is equivalent to 100 newtons per meter squared, or 100 pascals. This slide includes some unity brackets used to help structure conversions from one quantity to another. We considered unity brackets in a separate presentation outlining their structure and their application. On this slide we show specific conversions using unity brackets from meganewtons per meter squared to newtons per millimeter squared, from pascals to newtons per millimeter squared, from the bar to pascal, and from newtons per millimeter squared to the bar. Also included for reference the conversion from meters cubed to litres. They're all particularly relevant to mechanical engineering and specifically within this presentation fluid mechanics. I'll let you review these unity brackets at your own pace. Let's consider pressure P in a fluid. So pressure in a fluid has the following important characteristics. Firstly, pressure at any point in the fluid is the same in all directions, as shown in figure 5. So figure 5, the pressure in the fluid around the submarine, which is at depth h from the free surface, is the same. So each of the arrows shown here relate to the same magnitude of pressure that's assumed to be acting all around the submarine. And characteristic 2, the pressure exerted at this point, the location of the submarine below the surface, is always normal to the surface. So in other words, each of those arrows, when you view them, they're always at right angles to the surface of the submarine. Pressure P in a fluid continued. Figure 6, shown here, is another illustration showing equal pressures acting on all surfaces of a very small body that's immersed in the fluid. Here's our immersed body in the fluid, and again the pressures that are acting on this body at this depth in the fluid would be the same pressure. And again the pressure everywhere is normal, right angles to the surface. So each of these arrows are at right angles to the surface of the immersed body. And of course that's also true for the pressure exerted by the fluid on the container. Again, everywhere is normal to the vessel wall. And this pressure here is at right angles to the vessel wall. So very important characteristics to be aware of when analysing later fluid mechanics problems. Let's consider mass density. So mass density, usually denoted by the Greek symbol lowercase rho, shown here, is defined from the equation shown here. The mass density rho is equal to the mass of the fluid divided by the volume. Using SI units, mass would be in kilograms, volume be stated as meters cubed. So the unit of mass density in this particular case is the kilogram per meter cubed. Now for reference, the density of water is very important, and I would strongly encourage you to remember this value. So water density, denoted as rho of water here, is 1000 kilograms per meter cubed. Note that can be written as 1 megagram per meter cubed, or 1 ton per meter cubed, or indeed 1 kilogram per litre. And from my experience of industry when encountering fluid mechanics type problems or specifications that relate to fluid mechanics, is that there are often a range of units used. So it's very useful to be exposed to the range of units used for density. Again, referring back to the unity brackets, I've showed here different units of mass density, our symbol rho, again for your reference. So converting kilograms per meter cubed to a ton per meter cubed, unity bracket shown here. Converting kilogram per meter cubed into megagram per meter cubed, unity bracket shown here. converting kilograms per meter cubed into grams per centimeter cubed. That's sometimes a unit used within fluid mechanics. 2 unity brackets were used for that conversion. So note from the above unity bracket calculations that a mass density of 7,840 kilograms per meter cubed, that would be a typical mass density for steel, can be written as 7.84 tons per meter cubed, or written as 7.84 megagrams per meter cubed, or written as 7.84 grams per centimeter cubed. So each one of those values relates to the same mass density for a typical steel. And something further to note for reference, the relative density of steel in this case would be 7.84. So the magnitude of the various densities here actually relate to the relative density. Let's consider relative densities, symbol sigma, of liquids and solids. So the relative density of a solid or a liquid is the ratio of its density to that of water density at 4 degrees C and standard atmospheric pressure. So relative density, symbol sigma, is the density of our substance, for example, density of a liquid, divided by the density of water. Just note for reference, relative density will have no unit. It is a ratio of densities. Let's consider relative density, symbol lowercase sigma, for gases. So the relative density of a gas is the ratio of its density to that of air at standard atmospheric temperature and pressure. So relative density sigma of a gas is the density of our substance, gas in this case, divided by the density of air. The illustrative sketch on the right hand side, the reference to which I unfortunately do not have, shows how mercury, a liquid, has a greater density than water, and in this case as oil is floating on the water, it must have a lower density than that of water. Then we have a solid block of cork, which is floating on the oil, so it has a lower density than the oil. The illustration then shows gas butane, having a greater density than that of air, and gas methane, having a density lower than that of air. Example 1, part 1. If the relative density of petrol is 0.8, we've got to calculate its mass density. And part 2, if the mass density of helium is 0.178 kilograms per meter cubed, we've got to calculate its relative density. The question allows us to assume the mass density of fresh water is 1000 kilograms per meter cubed, and the mass density of air is 1.293 kilograms per meter cubed. Here are the relevant formulae for your reference. I'd encourage you to now stop the presentation and attempt example 1, but the full solution is shown on the following slide. So example 1 is the solution. So for part 1, we're given the relative density of petrol, it's 0.8. We're asked to calculate the mass density of the petrol. Relative density of petrol, that's equal to the mass density of the petrol divided by the density of water that we're given in the question. Simply transposing the equation, so multiplying both sides by the density of water, the mass density of petrol is equal to the relative density of the petrol multiplied by the density of the water. Inserting the values given in the question. The mass density of petrol is 800 kilograms per meter cubed, or that could be written as 0.8 megagrams per meter cubed. In part 2 of example 1, we're given the mass density of helium, 0.178 kilograms per meter cubed, and this time we have to calculate the relative density. So for part 2, relative density of helium will be the mass density of helium divided by the mass density of air, so again given in the question. Inserting the values, the relative density of helium is 0.1377. Again, note there's no unit associated with relative density. It's purely a ratio. Here's exercise 3 for you to attempt. Firstly, we have to calculate the mass density of alcohol, given the relative density of 0.81. And then we have to calculate the relative density of mercury, given the mass density of 13,600 kilograms per meter cubed. Answers are shown in the bracket here. I'd encourage you to start the presentation and attempt exercise 3, but I'll show you the full solutions on the following slide. Here's exercise 3, the solution. I'll let you review this at your own pace, but essentially the mass density of alcohol evaluates to be 810 kilograms per meter cubed, and the relative density of the lead evaluates to be 13.6. Again, note no unit associated with relative density. It's a dimensionless quantity. Exercise 4. We're asked to complete the missing entries in the tables below. The left-hand table here we have listing of solids or liquids. Liquid would be water, paraffin, solids aluminium, copper, etc. And we're asked to state the densities, both the mass density, kilograms per meter cubed, and the relative density. So we need to fill in the various blanks in the table. And on the right hand table we have gases such as air, argon, etc. And again we have to determine the values to complete the table. I would encourage you to start the presentation and complete exercise 4. Answers are shown in the brackets, and I'll show you the full solutions on the following slides. Here's exercise 4, beginning of the solution. This slide relates to the solids and the liquids, shown in the previous table. And I'll let you review the answers at your own pace. Just notice, of course, that the relative density of water will be 1 because it's relative to itself. So 1,000 divided by 1,000 is 1, of course. And here's exercise 4, solution continued. Here are the answers for the gases. I'll let you review these answers at your own pace. Let's consider the quantity termed specific weight or weight density, usually symbol lowercase w. So specific weight of a substance is its weight per unit volume. Since weight of the substance is the mass multiplied by gravitational acceleration, symbol g, usually assumed to be 9.81 meters per second squared, then the relationship between specific weight and mass density, symbol ρ, is as stated below. Specific weight is equal to the mass density multiplied by gravitational acceleration. In symbol form, that's lowercase w is equal to ρ multiplied by g. Specific weight, continued. So here's example 2. Part A, we're asked to calculate the specific weight of petrol if the relative density is 0.8. And part B, we're asked to calculate the mass density of copper if the specific weight of copper is 83.4 kilonewtons per meter cubed. I would encourage you to start the presentation and try and attempt example 2, but I'll show you the full solution on the following slide. So here's example 2, full solution. So in part A, we have to calculate the specific weight of petrol, given the relative density is 0.8. So in this case, specific weight W is equal to the mass density of the petrol. So I've multiplied the 0.8 relative density by 1,000 kilograms per meter cubed for the density of water. And I simply multiply that by the gravitational acceleration of 9.81 meters per second squared. So the specific weight of petrol is 7,848 newtons per meter cubed. And part B, we've got to calculate the mass density of the copper, the symbol ρ. And in the question, we're given the specific weight of the copper. 83.4 kilonewtons per meter cubed. So basically I've rearranged the above equation of W equals to rho G, divided both sides by G, so the rho is equal to W divided by G. Insert in the values. Just notice that 83.4 kilonewtons per meter cubed is actually 83,400 newtons per meter cubed, and divide that by 9.81. So the mass density of copper is 8,502 kilograms per meter cubed. Exercise 5, we'll let you attempt this. Part 1, we have to determine the specific weight of water. And in part 2, if concentrated sulfuric acid has a relative density of 1.84, we've got to determine the specific weight. The answers are shown in the bracket here for your reference. I would encourage you to stop the presentation and attempt exercise 5, but I'll show you the full work solution on the following slide. Exercise 5 solution, but for part 1, the specific weight of water is 9,810 newtons per meter cubed, or as the answer stated in the question, 9.81 kilonewtons per meter cubed. And for part 2, specific weight of the acid in this case, so that's the relative density 1.84 multiplied by the density of water, 1,000 kilograms per meter cubed. Remember that liquids are always relative to water. And then we multiply by 9.81 meter per second squared. So essentially this is still mass density here, rho, multiplied by G. Evaluating the specific weight of the acid is 18.05 kilonewtons per meter cubed. Let's consider exercise 6. The cylindrical fuel tank on a lorry is 0.5 meters in diameter and has a length of 1.5 meters. What will be the weight of the fuel when it's full? We're given the relative density of diesel oil is 0.86. We're also given the formula for the volume of a cylinder. V is equal to 1/4 pi d squared L. The weight force is shown in the bracket here. If you think you can attempt exercise 6 without further assistance, I'd encourage you to stop the presentation and do so now, but I will outline the solution on the following slides. So exercise 6, here's the beginning of the solution. As with all questions, we firstly extract the information from the question. The diameter of the fuel tank is 0.5 meters, so D 0.5, my sketch here. The length of the fuel tank is 1.5 meters, so L is 1.5 meters, again added to my sketch. And the relative density of the diesel oil is 0.86, so lowercase sigma 0.86. So there's the information extracted from the question, and as always I'd encourage you to draw a simple sketch showing the information we've extracted from the question. Exercise 6, solution continued. So firstly I've calculated the mass density of the oil, symbol rho here. And because this is a liquid, then the density of the oil is relative to water. So to calculate the mass density of the oil, multiplied by the mass density of water, 1,000 kilograms per meter cubed. So the mass density of the oil in this case is 860 kilograms per meter cubed. Next I've calculated the weight density or specific weight of the oil, simple lowercase w, and w is simply equal to the mass density from above multiplied by gravitational acceleration. So that's 860 multiplied by 9.81 meters per second squared. So now we have the weight density. I've next calculated the volume of the tank, capital V, and we know that V is equal to pi d squared upon 4 multiplied by L, area times length in other words. Inserting the diameter into the equation, 0.5 meters, shown in the sketch here, and the length of 1.5 meters. Then the volume evaluates to 0.295 meters cubed. So finally calculate the weight of the oil, capital W, weight is equal to the weight density, lowercase w, multiplied by the volume of the tank. Inserting the values, the weight of the oil is 2,489 newtons. That concludes exercise 6 solution. Exercise 7. A hydraulic cylindrical shock absorber has an internal diameter of 10 centimeters and is 1.2 meters in length. The shock absorber is half filled with hydraulic oil and half filled with nitrogen gas at standard atmospheric pressure. We're asked to determine the weight of the nitrogen and the weight of the hydraulic oil contained within the shock absorber. We're given the relative density of nitrogen gas and hydraulic oil as 0.97 and 0.85 respectively. The weight of the nitrogen and the weight of the hydraulic oil stated in the bracket here. Again, I would encourage you to start the presentation and attempt exercise 7, but I'll show you the full work solution on the following slides. Exercise 7, solution. Extracting the information from the question, we know the internal diameter of the shock absorber, capital D here, is 10 centimeters. Converted that into meters, 0.1 meters. The length of the cylinder, or length of the tank here, capital L, 1.2 meters. And the relative density of nitrogen, 0.967. So sigma for nitrogen is 0.967. And the relative density of the oil is 0.85. Sigma for the oil, 0.85. Notice that the tank of the shock absorber is 1.2 meters in length, but split into two sections. So the nitrogen part of the tank is 0.6 meters, and so is the oil part of the tank, 0.6 meters. So there's my information extracted from the question. So exercise 7, solution continued. I'll just briefly outline the solution and then let you review the calculations at your own pace. Initially, we calculated the full volume of the tank, capital V here, stated in terms of pi, that's the exact answer, and also to 3 significant figures here. But we know in the question the tank is split into 2 sections, each 0.6 meters in length. So I've actually calculated half the volume of the tank, lowercase v here, again stated the exact answer, and the answer to 3 significant figures. Next, I've calculated the mass density of the nitrogen, using the symbol rho here. So that's the relative density of the nitrogen multiplied by the mass density of air. That produces our density in kilograms per meter cubed. To find the weight force of the nitrogen, symbol capital W here, is simply the mass density from above multiplied by the volume of half a tank multiplied by gravitational acceleration. So that evaluates to 0.0578 newtons. So that's the weight of the nitrogen in the cylinder. We then undertake similar calculation to find the mass density of the oil, rho of the oil here. So this time we're using the relative density of the oil multiplied by the mass density of the water, because oil is a liquid, so that's relative to the density of water. Nitrogen was a gas, so that's relative to the density of air. Multiplying the relative density of the oil by the mass density of the water, we evaluate the mass density of the oil in kilograms per meter cubed. So finally we can find the weight of the oil, W of the oil here. That's the mass density of the oil from above, multiplied by volume of half the tank, multiplied by gravitational acceleration, and that evaluates to the weight of the oil of 39.294 newtons. And finally, purely for reference, I've calculated the total weight, capital W, of the shock absorber, which is the weight of the nitrogen added to the weight of the oil. But that's purely for reference. Within the solution, I've not referred to specific weight, but I know that some students prefer to use specific weight within their calculations, and that's absolutely fine. And here's the bibliography used to help generate this presentation. which I hope has been of interest to you, and thank you for viewing.